Welcome to The Explainer. Today, we're going to break down one of the most fundamental software design patterns out there, the factory pattern. It is an absolutely essential tool for creating objects, and we're about to see exactly why it's so powerful. Okay, so to really get this, let's start with a problem that you've probably seen or maybe even written yourself. It all comes down to that little three-letter keyword, new. All right, check this out. It's a super common situation. Your main code needs a specific tool to get its job done. In this case, an iterator to loop through a playlist. And the most direct way to do that is right here. You just use the new keyword to create a linear iterator right on the spot. I mean, it's simple, it's quick, and hey, it works. But as we're about to find out, this direct approach comes with some pretty serious hidden costs. So on the surface, this looks totally fine, right? Simple enough. So what's the problem? Well, the problem pops up the second your application needs to change or grow. What happens when you need a different kind of iterator, or a brand new one you haven't even thought of yet? This is where the cracks in this simple, direct approach really start to show. And here's the thing. Creating objects directly like this makes your code brittle. Your main code is chained directly to that specific linear iterator class. We call this tight coupling. The two pieces of code are basically stuck together with superglue. So if you suddenly decide you want a random iterator instead, you have to go into your main logic and perform surgery on your code. This brittleness means a simple change request could turn into hours of hunting through your code base, and that just opens the door to introducing new bugs every time you make a change. It's not a great place to be. You know, to really wrap our heads around the solution, let's just forget about code for a second. Let's think about something we all do, a simple, everyday task. This is going to make the whole pattern just click. Okay, so let's say you need a pen. Simple enough. Now, how do you get one? You don't get in your car and drive to the pen factory, right? You don't go and ask the workers to start molding the plastic and injecting the ink for you. Of course not. That would be completely inefficient, just crazy. Nope. Instead, you go to the supermarket, a central, convenient place that has already handled all the complicated stuff for you. It's a one-stop shop that has sourced all the different kinds of pens you could possibly want. You just walk over to the stationery aisle and boom, there they are. All the options laid out right in front of you. You don't care how they were made or how they got there, you just pick the one that fits what you need to do. Now, here's the really interesting part. Think about your shopping bag. Does it care if you picked a ballpoint or a fancy ink pen? Not at all. It's designed to hold a pen. It doesn't need to know the brand or the type. It just needs to hold something that can write. And that idea, that's huge. So this whole supermarket trip, it's actually a brilliant illustration of the factory design pattern. The logic we naturally use for shopping translates directly into a much cleaner, more flexible way to write code. Let's just map it out. Okay, so here's how it all lines up. The supermarket, that's our factory class. The one single place that's responsible for creating all the objects. The general idea of a pen, that represents our interface. It's like a contract that just says, hey, this thing can iterate. The specific types, like the ball pen or the ink pen, those are our concrete classes. And you, the customer, you're the client code, the part of the program that needs an object, but really shouldn't have to care about the messy details of how it's actually put together. So let's get back to it and see how this transforms our actual code. Honestly, the difference is like night and day. So on the left, you see our original fragile code. The client is messy, it's rigid, and it's tightly coupled to every single iterator type. But look at the code on the right. See how clean that is? The client just makes one simple call to the iterator factory and asks for an iterator. All that messy creation logic is now hidden away, neatly contained inside our factory. And the process is just beautifully simple. First, our client code requests an object from the factory, telling it what kind it wants. Second, the factory has all the smarts, all the if-else logic, to figure out which specific class to build. Third, it returns that brand new object. And fourth, our client uses the object through that common interface, with zero knowledge of whether it actually got a linear iterator or a random iterator. It just works. So our code is much, much better now. It's way cleaner, way more flexible. But this simple factory design, it's not perfect. In fact, there's a hidden flaw here that actually violates a very important design principle. Let's go back to our analogy for a minute. Imagine a brand new type of gel pen just hit the market. What has to happen behind the scenes for that new pen to actually appear on the shelf for customers to buy? And that's the issue. To support a new reverse iterator, for example, we have to go back and crack open the iterator factory class itself and physically add a new else-if statement to its logic. We are literally modifying existing working code. This directly violates a key solid principle, the open/closed principle. And the idea is actually pretty straightforward. It says our code should be open for extension, meaning we should be able to add new functionality, but closed for modification, meaning we shouldn't have to change existing code that's already been tested and works perfectly fine. So this leaves us with this fascinating challenge, right? How can we design a factory that can learn to produce new things it has never seen before without ever having to shut down and retool the assembly line? Is it possible to build a system that's truly open to the future? Well, that is the question we are going to answer next time.